So students, we will be discussing today regarding groundwater, its characteristics, and how to estimate the quantity of groundwater from a particular area under the ground. So here is a picture, combined picture of surface water and groundwater. As you can see here, the upper portion of the diagram where the trees and the surface water is showing, and the dotted blue line here is showing the natural water table which lies below the ground. So the upper portion of the water table is named as unsaturated zone because here all the void spaces are not filled with water, but below the water table all the void spaces in the soil or in an earth content, it is filled with water, so it is named as saturated zone. And this in this saturated zone, the water which is filled in the void spaces, void pores, is named as groundwater. So in the below bottom portion of the diagram, we can see here in the left hand portion that the cracks or the fissures in the rock is sometimes filled with air and also with water. Light blue color is depicting the content of water. So water, it is not groundwater, held by molecular attraction surrounds surfaces of rock particles. Right hand side also we can see here the blue color is showing the water, but it is not groundwater. It is the water that is held by molecular attraction of water itself in the rock or in the void spaces of gravel. This dotted line is showing the level of water table. Under the water table area, the area under the water table on the left hand side and on the right hand side, all the void spaces are filled with blue color, that means groundwater, and all the openings below the water table will be filled with groundwater. So where we can get this groundwater and what it is named in technical, in engineering term, it is named as aquifer. Geologic, it is a geologic permeable formation. But basically it is a geologic formation. In nature it is permeable, which permits sufficient quantity of water under ordinary conditions like in sand and gravel. Under ordinary condition, natural conditions, it will permit the area or the depth of the geology will permit sufficient quantity of water to flow. Types are confined and unconfined water table. So the types also named as types of aquifer also named as artesian and water table. Artesian, we will discuss it in the next few more slides. Artesian means the confined. The aquifer area, the aquifer depth is confined between two layers, and sometimes this aquifer zone or depth is confined in one layer at the bottom. So it is named as water table. Unconfined aquifer is that type of geologic formation where the upper surface is the natural groundwater table, as we see before in the earlier slide. Water table varies in undulating slope. Obviously, water table will not be constant or at a fixed level everywhere. It will vary according to the ground level and according to the geologic formation of various areas, and it will be a undulating level or slope. Due to this, there is a change in water storage volume. Where the level is high, the water storage volume will be more. Where the level, groundwater level, water table level will be less, there the water storage volume will be less naturally. But in the confined aquifer, groundwater is confined under pressure greater than atmospheric pressure, so overlying by impermeable strata. So it can be differentiated like that. In the unconfined aquifer, the top level is known as natural groundwater table, and it is confined, it is fixed with some impermeable strata at the bottom. And in the case of confined aquifer, the top and the bottom of the confined aquifer layer is confined with some rock, impermeable strata like rock or heavy boulder or gravel, and in between the void spaces or void spots are filled with groundwater. So in the confined aquifer, groundwater is confined with a pressure which is not open, which is not atmospheric pressure, but it is greater than atmospheric pressure. So in the aquifer, when we will penetrate or we will install a well, then water level will rise to the local static pressure. Water level will rise. It will rise to the local static pressure. We will see diagrammatically in the next slide. When water is withdrawn from the by the help of the well, or you can visualize it by the help of the hand pump, a depression in the piezometric surface occurs. Piezometric surface means water table level. So when we will withdraw some quantity of water from this well, automatically the level of water will reduced, so a depression will occur. This decrease or depression in pressure causes expansion in water, sometimes compaction of aquifer. So pressure is decreasing, and so water, the water in the void spaces will be expand, and it will give an effect, compaction effect actually, on the aquifer area. So here is a diagram where we will see that confined and unconfined aquifer is combinedly showing. Like here it is a piezometric surface, natural piezometric surface, and here also C, named as C, A and B, three well is are penetrated in confined area. So it is, this zone is named as confined area because here at the bottom here is also an impermeable strata, and at the top also here it is a confining layer, means also no water will get away or get conveyed through this confining layer and impermeable strata. Only water will flow through this confined aquifer. And above this confining layer, this is an unconfined aquifer, where the top layer is known as, the top layer will consist as or confined as water table, confined by the water table, natural water table. So here also a well is penetrated named as C, here also A, and at the right hand side here also it is named as B. So water table well, this well, C well is named as water table well. A well is also named as water table well or flowing well, because here water is naturally coming out. Now water is naturally coming out from the well, so it is named as flowing well. This layer is showing the ground level, earth level actually. At the well B, ground level is here and water level is here. So in this case water is not flowing, is not coming out naturally, is not flowing, so it is named as only artesian well. And in this well, where it is confined, this well is penetrated or installed up to the unconfined layer or unconfined aquifer. Like A, B or C, it is not going to the confined aquifer, it is only restricted to the unconfined aquifer. So here this is also named as water table well, like here also water table well, and some water will rise in the well from the circumference of the well, and water, when we will pump out this water, here a depression, and we can see the decrease in the pressure will cause. So what is flowing well and artesian well? When a well penetrates here in the red circle at the well A, when a well penetrates a confined aquifer and water will rises to a local static pressure. If this pressure is sufficient, to raise the water level above the ground, to raise the water level means it is coming out naturally over the ground, above the ground, flowing well, this condition will be named as flowing well. But if the water level is below the ground level, in the case of B, but above the local water level, here is the water level, it will rise to this point, but it is below the groundwater, this condition will be known as artesian well. Here a third type of well, which is very rare actually, we can see here, sometimes a lanes or localized area, patch area or of impervious strata can occur inside an unconfined aquifer in such a way that it retains a water table above the general water table. So here we can see that a local area, a small localized area of impervious strata can occur, can happen, like in the diagram you can see, inside an unconfined aquifer. Here it is an unconfined aquifer zone. In between the unconfined aquifer, a small portion of impervious strata, means you can visualize it as rock or gravel layer. It can be happen naturally in such a way that it retains some water, means it retains a water table above the general water table. So general water table is here, it is shown here, but some portion of water is retained here. Such a water table retained around the impervious material is known as purged water table. Usually, this purged water table is of limited extent. It means for a smaller area, limited area, and the yield from such a situation is very small. It means the output, if we install or penetrate well in this area, in this zone or depth, we will get this impervious strata and we will consider it that it is the strong foundation. So we will penetrate the well up to this level. But here water is of limited quantity. So we will pump out, when we will pump out, we will get a limited quantity of water. So the yield will be less. In groundwater exploration investigation, a purged water table is quite often confused with a general water table. So an engineer or workers may be confused that this area, in this area, from this area we will get a small quantity of water, but here the actual quantity, actual level of groundwater table is here, where we can get so much quantity of water. So it is we can call it as a confused or confusion in the water table in the case of purged water table, which is which generally occurs in unconfined aquifer zone. So same, this diagram is also showing the same artesian well, flowing artesian well, where naturally water is coming out. Confining layer is actually impermeable, with impermeable characteristics, and it is shown here with brown color. And water table well is here in a confined aquifer, where we can get water by pumping out from the well. So now we are coming to the aquifer properties. We have to know some characteristics and properties of particular geologic formation. Means we are considering here it is an aquifer here, to estimate the quantity of water present in that area. So first is known as porosity. Some of the properties are same what actually we have already studied or learned in the soil mechanics. So first is porosity. So volume of void space per unit volume of aquifer. Maximum water storage capacity where in the pore. So it is the maximum water storage capacity of a specific aquifer volume. Permeability. Ability of a rock, or maybe clay, maybe soil, maybe sand, to transmit or pass the water through it. Specific yield. Some water in the pores are retained by molecular attraction and surface tension, as we have seen in the first 2-3 slides. The actual volume of water that can be extracted by gravity, so not by, it is retained by molecular attraction, and from that the actual volume of water which can be extracted by gravity only from an unit volume of aquifer material is known as specific yield, and it is denoted by SY. Another property is known as specific retention. Yield means outcome which we can get. So the second one is known as specific retention, which can be retained back. The quantity of water that held back or retained in the aquifer zone against the gravity is known as specific retention, denoted by SR. So specific retention means the quantity of water that will be retained, not extracted, in the from the particular aquifer zone against the gravity. So some portion will be extracted, can be extracted, and some portion will be retained back. Both, if we combine the both quantity of water or volume of water, we will get the total volume of water which is there as storage capacity in from a unit volume of aquifer, and it is known as porosity. So at the bottom it is written as porosity equals to specific yield plus specific retention. Another term is known as storativity or storage coefficient. It is simply denoted by capital S. Volume of water which is released or can be taken by, which is released by or can be taken by into a column of confined aquifer of unit cross-sectional area under a unit decrease in piezometric head. So in the diagram below we can see the piezometric head. First at the initial, the piezometric surface head is here, and under a decline of unit decrease, unit measurement, suppose 1 meter in the piezometric head from a unit area of column in the aquifer area. So it is a unit volume of aquifer, from where that quantity of water that can be released or can be taken is known as storativity. In the confined aquifer, it ranges between 0.00005 to 0.005, a small amount of water. In unconfined aquifer, here it is confined aquifer, both the top and the bottom layer is with impermeable strata or confining strata. But in the case of unconfined aquifer, where water table decreases, water table will be the topmost layer or level in the case of unconfined aquifer. When the water table will decrease by 1 meter, water drains under gravity. So in the case of unconfined aquifer, storativity actually equals to specific yield, which we have seen in the earlier slide. Next term is known as coefficient of permeability. It is much more known to you because you have already studied soil mechanics. So rate of flow or velocity of water through a unit cross-sectional area of aquifer under a unique hydraulic gradient. So it is the velocity of water through a unit cross-sectional area in the aquifer under a unique hydraulic gradient. So here the unit of K, capital K, coefficient of permeability, is centimeter per second because it is a rate of flow. So the equation of K is, it varies with the porous media, means aquifer property, size or grain size, you can consider it as a particle size or grain size of the aquifer and with the fluid property. So if we equal the K with the porous media, d square and fluid property, we will get a constant C. So C is known as shape factor, and it depends on the porosity, shape of particle. Maybe it generally it considered as spheroid or spherical particle shape. Here T is mean particle size in the aquifer. Gamma is known as, actually we know, unit weight of water, and mu is known as dynamic viscosity of the water. So K, standard K, is known for pure, we know at for pure water is, if standard K we will consider, it is for standard temperature 20 degrees Celsius, and for different other temperatures we will get like Ks by Kt equal to, Ks means K standard by K at different temperature equals to nu T by nu S. K also known as K naught into gamma by mu. So K naught is actually named as specific permeability or intrinsic permeability. It is only depends on the medium property, means the aquifer medium property. C is shape factor and T is the mean particle size of that aquifer. And gamma by mu is known as fluid property, unit weight of water and dynamic viscosity. At 20 degrees Celsius, nu of water is generally taken as 0.01 centimeter square per second. So by lab test, by permeameter, constant head permeameter for coarse soil and for fine soil falling head permeameter, we can estimate the coefficient of permeability K. Also by field test like pumping test in a well, or by using dye or tracer content, we can estimate the coefficient of permeability K for a particular aquifer zone. Now we are coming to the next term, which is known as transmissibility. So transmissibility is depicted by capital T, and it is the ability of rock or soil or clay to transmit or pass the water through it. So at the initial, we judge or we consider that transmissibility almost same as permeability. It is same as permeability, but with a different mathematical meaning, and this difference, the difference in mathematical meaning, is introduced by scientist Thies. So what he had told, that the flow or discharge of the water through an aquifer of unit width and full depth is here depicted, denoted by capital B, under a unique hydraulic gradient. So T is the flow or discharge of water through an aquifer of unit width and full depth, not unit depth. It is of unit width and full depth under a unit hydraulic gradient. So T is equals to, we can write it down in an equation form like T equals to K into B. B is the full width, full depth, and into 1 means unit width, and K is the permeability, coefficient of permeability. So here the unit of T is meter square per second. K 1 meter from K, and for depth also we will consider meter. So here is meter square per second. Well, when we construct or install a well with T equals to 1 into 10 to the power 5 per meter width, it will be satisfactory for irrigation, where the water will transmit or pass through from that aquifer area. For different layers of aquifer, maybe there are different type of permeability. So stratification of permeability, here one term is occurring. So aquifers may be stratified in layers with different permeability. So when flow in parallel to layers, when the flow will be in parallel to layers, the equivalent permeability Ke equals to summation of Ki into Bi. B means full depth of the aquifer. Ki means for B1 it will be K1, for B2 it will be K2, and the equivalent permeability Ke is equals to summation of Ki into Bi divided by summation of Pi, and in that case T will be equals to Ke into summation of Pi. But when the flow is normal to the layers, means the flow is vertical to the different aquifer layers where the permeabilities are different, equivalent permeability Ke will be equals to summation of Li, it is the length, summation of Li divided by summation of Li by Ki, and in that case transmissibility will be Ke into total full depth P. Here the different layers we are not considering, we are considering different length of flow, different length of the layers, not depth. So now we will see what is happening when a well is penetrated or installed and pumping is carried out by the help of well. What will happen in the groundwater area, which is actually in a aquifer zone. So first, wells are the forms most important which will give us the major quantity of water from groundwater table or groundwater area from an aquifer for supply of water for domestic purposes or maybe for irrigation purposes. So first we can consider that the water is in an unconfined aquifer being pumped at a constant rate from a table from a well. So as we know, in the unconfined aquifer, water table will be at the topmost level. Prior to the pumping, the water table in the well, the water level actually in the well indicates the static water level, means it is with the local static pressure. A lowering of this water table will take place on pumping. So when we will start pumping, the water level inside the well will lower down, will decrease with time. If we consider the aquifer is in homogeneous nature with not different characteristics, same, isotropic means will not change in place or time, and the water table is horizontal initially Actually, the water table will not be horizontal, it will be with undulating slope, but we will considering here the water table with horizontal initially. Due to the radial flow into the well through the aquifer, the water table assumes a conical shape named as cone of depression. So if we consider the aquifer is in homogeneous nature, isotropic, and water table is in horizontal level and pumping is going on, then from the surrounding aquifer here, water will radially flow into the well. And in this case, water table will be in a shape of a cone, which is actually known as cone of depression. Depression means down, decreasing in the water level. So it will create a cone of depression. The drop in the water table elevation means water level at any point from its previous static level, initial static level, is named as drawdown. Means the decreased level from H1 to H2 maybe is the drop in the water table due to the pumping, and it is named as drawdown. The areal extent means the area of the cone of depression up to which distance you can say from the center of the well the cone of depression will happen. So the areal extent of the cone of depression is known as area of influence. Up to that portion, up to that distance, maybe 10 meter, maybe 100 meter, maybe 500 meters, the influence, it will be the influencing area of the well when pumping is going on, and the radial extent is known as radius of influence. So at constant rate of pumping, when we are pumping for a much longer time with a constant rate, a drawdown curve will develop gradually. A drawdown will develop, and if we join at different points at different distances, it will give a drawdown curve with time due to the withdrawal of water. This phase is known as unsteady flow, as the water table will gradually lowered at a given location near the well, and it will change with time, it will lower down with time. On prolonged pumping means for a more longer time, an equilibrium, if the pumping is going for a more longer time, an equilibrium state is reached where the rate of pumping and rate of inflow of groundwater from the outer edges of the radius of the zone of influence will occur. So how equilibrium state will be attained? Rate of pumping and rate of inflow of groundwater into the well from its surrounding area, from its zone area of influence will occur. The drawdown surface attains in this equilibrium state. The drawdown attains a constant position, means the water will not go further down in the well. With respect to time, when the well is known to operate under steady flow condition. So first an unsteady flow condition will occur, and with time when an equilibrium state will reach, a steady flow condition will be attained in the well, where the drawdown or the decrease in the water table will not happen further. So here it is here is a diagram which will show the occurring of drawdown and what is happening actually when we are installing a well and pumping is occurring. So here pumping is occurring from a well and it is filled with blue colored water. The natural groundwater table is shown in blue color. Groundwater will flow when for prolonged pumping. The groundwater flow from the area of influence to the well, and from here from the well we can get the water in a sufficient quantity. As soon as the pumping is stopped, the depleted storage in the cone of depression is filled by groundwater inflow into the zone of influence. When the pumping is stopped, actually the depleted storage means the water which is decreased from the storage, means which we have taken out by pumping in the cone of depression area or cone of the influence area, it is filled by the groundwater inflow from the area of influence. So there is a gradual accumulation of storage till the original static level is reached. In this condition, automatically, naturally, the groundwater will flow into that particular area from where we have pumped out the water. Accumulation of storage will happen until the original level is reached, water level is reached. This stage is named as recuperation or recovery of water table, and it is a unsteady phenomena. Recuperation, the time required for recuperation or recovery will depend upon the aquifer characteristics. The same condition also develops in confined aquifer, also with the difference that the piezometric surface instead of water table we have considered in unconfined zone, but in the confined aquifer we have to consider the piezometric surface that changes the drawdown with the development of cone of depression. So now we will see what is happening hydraulically, means mathematically we will express this situation what we have seen in the earlier slides, that what will happen and how the quantity of groundwater which we are actually pumping out will differ in the confined aquifer and unconfined aquifer. So here first we will know about Darcy's law. Darcy's law is applicable in the for the flow of any fluid, in this case it is groundwater, through a soil. So according to Darcy's law, rate of flow or discharge is proportional to the hydraulic gradient. So first V is proportional to hydraulic gradient I. I is we know I is equals to delta H, change in H, height, upon L, in the distance of aquifer. So V is proportional to I. For laminar flow, Reynolds number Re equals to rho Vt by mu equals to nu Vt by nu, which is less than equals to 1. Reynolds number is less than equals to 1 in case of laminar flow. So when we will multiply a constant with hydraulic gradient I, we will get V equals to K into I, and here K is the coefficient of permeability we are using or considering. Now we know that Q equals to A into V. So if we write down Q, then A will introduce and we will write it down in the place of V, K into I. So Q equals to KIA, where K is coefficient of permeability, meter or centimeter per second. I is hydraulic gradient, delta H by L or dH by dL. H is piezometric head. L is distance in flow direction in the aquifer zone. So when a well is penetrated and water is pumped from that well, it means water will flows toward the well from the surrounding area of influence from the storage. So the piezometric head will decline or decrease, which will form a cone of depression. We will see in the next slide in a particular diagram. The amount of decline is known as drawdown, and if we join the drawdown points for various radius or radius of influence, it will give a cone shape which is known as drawdown cone. The time required to reach the steady state depends on the storativity, depends on actually the aquifer characteristics, properties like storativity, transmittivity, the boundary conditions and the pumping rate. Monitoring the development and the final form of this cone in observation wells around the pumping well gives us the determination of aquifer properties, which is mainly storativity S and transmissivity T. So assumptions we are taking here, that aquifer is homogeneous, isotropic, the areal extent is infinite, and K and T are constants. Coefficient of permeability and transmissibility are constant. Pumping well will fully penetrate into the aquifer zone depth, means in case of both the cases, confined and unconfined aquifers, and it will receive water from the entire thickness, the entire depth or thickness of the aquifer. Transmissivity, capital T, is constant in space and time. Pumping is continued at a constant rate long enough for steady state to prevail, so that equilibrium condition will be reached. Flow lines are radial, horizontal and in laminar condition. Inclination of water surface is small, means water level, the drop down, the slope which is happening with the drawdown of the water table is small, and Darcy's law is valid. Under these assumptions, so H2 minus H1 means this quantity is actually, we can write it down as S1 minus S2. So H2 minus H1 will be equals to S1 minus S2. For small drawdown, H2 and H1 both are equal to T. For small drawdown, we can consider here, we can assume or we can consider here that both H1 and H2 will be equals to D. D is the full depth of the aquifer. So we can write it down here like H2 square minus H1 square means H2 plus H1 means 2D into S1 minus S2. Otherwise, we can also write it down that T equals to K into D. We know transmissivity equals to coefficient of permeability into the full depth of the aquifer. So coming back to the first green colored equation, we can write it down. Q equals to pi K into, instead of H2 square minus H1 square, we can write it 2D into S1 minus S2 and divided by 2.3 log 10 R2 by R1. Same 2D we can write it as pi, 2 will be constant, pi will be constant, T into K we can write it down as T. So second another equation is also colored here is in green. Q equals to 2 pi into T S1 minus S2 divided by 2.3 log 10 R2 minus R1. So according to the given data, whether H2 H1 is given or T is given or S1 S2 is given, we have to consider the equation for fastest calculation or estimation of Q, maybe from the basic equation in the red, or maybe in the green from the green colored equations. Now let's see what is happening in the confined aquifer. So in the confined aquifer, also given by Thiem, the assumptions, some of the assumptions will change and we have to assume like in another way, like the flow in the aquifer is actually radial and horizontal in the confined aquifer. We are assuming in the unconfined aquifer earlier that flow will the flow of water will occur radially and horizontally, but in actual case in the unconfined aquifer it will be not like that. So we are assuming there, but in the confined aquifer actually the flow will be radial and horizontal, because the confined aquifer is fixed with impervious strata at the top and bottom. So water will not go here and there and it will not flow to the bottom or to the upward direction. So flow will be actually horizontal and radial. So here we are not assuming it, it is actually happening. All other assumptions will be same in case of confined aquifer. So here is the main pumped well, same. At the observation well 1 is 1 and H1, observation well 2 is 2 and H2. Here the confined depth, aquifer depth, is denoted by capital H. Here the confined aquifer depth is denoted by H, capital H, and D, capital D, is the depth from the bottommost layer to the piezometric surface, is denoted by capital D. So here Q equals to same KIA, but here we will write K into dH by dr into 2 pi r capital H, because H here is the capital H is the height of confined aquifer. So dr by r equals to 2 pi k capital H, not small h, capital H divided by Q into dH. So in the same integration between limits R1 and R2 on the left hand side and H1 and H2 on the right hand side, we will see log E R2 by R1 equals to 2 pi k capital H by Q into H2 minus H1. So the final equation, basic equation of the Q in the confined aquifer is 2 pi k into capital H, which is height of the confined aquifer, total depth or height, into H2 minus H1. H2 and H1 is the water depth in the aquifer, divided by 2.3 log 10 R2 minus R1. If we consider here, you can see it on the right hand side, H2 minus H1 equal to S2 minus S1, S1 minus S2. Likewise, in the earlier case, we can write it as Q equals to 2 pi kh S1 minus S2 divided by 2.3 log 10 R2 minus R1. And if we write K into H is, we know, is transmissivity T, so final Q will be equals to 2 pi T S1 minus S2 divided by 2.3 log 10 R2 minus R1. So these three basic equations, red and two green colored equations, we have to use according to the data given in the numerical problem to estimate the yield or discharge or the quantity Q from the confined aquifer.